Welcome back to K11 Tech University. All right, so last time we did something pretty cool. We figured out how to use bitmasks to basically pack every possible combination of a set into single, neat little numbers. Today we're going to unleash them.
Think of it like this. In our last session, we basically forged the keys. Today, we're going to use those keys to unlock every single door, look inside every room, and figure out where the real treasure is hidden. This is the next and most crucial step. So, you might be wondering, why on earth would we want to generate all these combinations in the first place? Well, it turns out that a ton of real-world problems, I'm talking about everything from optimizing a delivery fleet to designing a new drug, it all boils down to one thing: finding the one perfect combination out of millions or even billions of possibilities. I mean, have you ever really thought about how your mapping app finds the quickest route during rush hour? It's not magic. It's grappling with these exact questions. It's sifting through an insane number of potential paths to find the one that gets you home the fastest. These questions are at the heart of so much of modern technology.
And this stuff is everywhere. It's the engine behind your company's scheduling software, it's how logistics companies manage their entire supply chain, and it's how developers test their apps to make sure they don't break. Honestly, understanding how to handle combinations is a genuine superpower.
Okay, so how do we actually do it? How do we methodically generate every single possible subset without missing any? Well, the method is actually beautiful in its simplicity, and it all comes back to those bitmasks we already know and love.
All right, here's the fundamental truth you have to wrap your head around. For any set with n items, there are 2 to the power of n possible subsets. Now, for small numbers, that sounds manageable. But as we're about to see, this number doesn't just grow, it explodes.
So the process is incredibly slick. Just imagine a counter. We started at 0, and we just count all the way up to 2 to the n minus 1. For each number along the way, we look at its binary representation, the pattern of ones and zeros. That pattern tells us exactly which elements are in the subset. A 1 means it's in, a 0 means it's out. It's that clean. Let's make this super concrete. Take a look at this table for a tiny set with just 3 items, A, B, and C. We just count from 0 to 7. The number 0 is 0, 0, 0 in binary. That's the empty set. The number 1 is 0, 0, 1, which means only the last item C is in the set. And if you go all the way to 7, which is 1, 1, 1, you get the whole shebang, A, B, C. See? A perfect one-to-one mapping. Now, why is this so great? Because when you're building a system, you need guarantees. This method guarantees you will never, ever generate a duplicate. It guarantees you'll get them in a predictable order every single time. There's no guesswork. It just works.
But let's be real, in almost every practical problem, we don't actually care about all the possible combinations. We're usually looking for a specific few that follow a set of rules. This is where we stop being a simple generator and start being an intelligent solver.
You know, you can't just pick a team for a project without considering the budget. You can't plan a road trip without thinking about how much you can spend on gas. These rules, or constraints, are what make problems interesting. They're what separate the good solutions from the bad ones.
So this is the big difference. Brute force is like trying on every single pair of shoes in a giant warehouse to find one that fits. It's exhausting and inefficient. A selective search is like going straight to your size on the shelf. We use the constraints to ignore all the junk we know won't work from the very beginning. So far, this all sounds pretty powerful, right? But I need to give you a serious reality check. There's a catch to this whole enumeration thing, a massive, unavoidable catch, and we need to face it head on. So, let's talk numbers. Let's say we have a set with just 20 items. 20! That doesn't sound like a lot, does it? But the number of subsets you have to check is already over 1 million. 1 million! Okay, a modern computer can handle that, but it's gonna take a moment. Now, what happens if we add just 10 more items? Just 10. We go from 20 to 30. Does the number of subsets double? No, it explodes to over 1 billion. From 1 million to 1 billion, that's a 1,000-fold increase from just adding 10 little items. This is the brutal, unforgiving nature of exponential growth. Just look at this chart. That is not a gentle slope. That is a vertical wall. Trying to brute force a problem of that size isn't just inefficient, it's impossible. Your program would run for days, maybe weeks, and never finish. And that leads us to probably the most important question a good engineer can ask. It's not, how do I write the code to do this? It's, can this even be done?
Before you write a single line of a for loop, you have to respect the numbers and ask if you're about to send your computer off a cliff. This whole discussion brings us to a much deeper point, something that's really about the difference between just coding and true engineering. It's about achieving what I like to call algorithmic maturity. If there is one thing you remember from today, I want it to be this quote. Algorithms are not just about writing loops. They are about respecting limits. Knowing the boundaries, knowing what is computationally feasible and what is pure fantasy, is just as important as knowing how to write the code itself. And this isn't some dusty academic idea. It's at the core of the most advanced systems we use today. When you ask an AI to generate an image, it's navigating a search space with more combinations than there are atoms in the universe. The only reason it works at all is because it's built on algorithms that are incredibly smart about respecting those insane limits. So if just checking everything is a dead end for any real problem, what do we do? How do you find that 1 in a billion answer without looking at all billion possibilities? Well, that's where the real art of algorithm design comes in, and that's exactly what we're going to tackle next time. Because that's the ultimate takeaway here. True expertise in this field isn't about being able to generate everything. It's about having the wisdom to know what you can safely ignore. This is K11 Tech University. I'll see you in the next lecture.